Welcome everybody to the Asia Pacific Analysis and PDE seminar. It's a great pleasure for me that we could get this joint seminar, this international seminar launched, in particular in this period, in this pandemic period, where so many travel restrictions are in place, and but we should not actually discourage us mathematicians or scientists from these kinds of restrictions. We should now start even harder, I would suggest. And for this reason, I asked so many organizers, and I'm very grateful for them that they accepted the invitation, that we start an international seminar running, like this one. So there are several of this kind, one world PDE seminars or one world probability seminars. However, the time is not really appropriate for the Asian Pacific region. And that's the reason why we created exactly this one, so that it is suitable for our time frame. Okay, so how it is organized is, so there is a group of organizers, and if you, for instance, as a participant would like to give a talk once because you have a strong result, then I please you to approach the organizers, which are on the web page of this seminar, and ask them whether you could give a talk. Okay, they will decide at the end whether it's possible or not. And you, of course, you approach the one who is in your field of research. Yeah, and the organizers, they will chair the session, in fact. So they choose the speaker and they will chair the session. And at the end, yeah, so at the end of everything, there will be a coffee break. So you will receive an email from me 50 minutes before this seminar will end, where you can please join again. And then all your faces, if you want, can be made visible and you can speak with each other, like in a normal coffee break, which is on a conference. Okay, now I give the word to Ben Andrews, who is the first organizer of our group, and to introduce the speaker of today. Thank you.
Thanks, Daniel. Thanks very much. And I'd just like to say thanks to Daniel for all the work he's put in setting this up. I hope it does something to bridge the isolation for all of us. So it's a great pleasure for me to introduce our first speaker. He's Chao Xia from Xiamen University, and he's going to speak on a topic which I'm very interested to hear about. The title is Recent Progress on a Sharp Lower Bound for the First Non-Zero Steklov Eigenvalue. Thanks, Chao.
Okay, thank Ben for the introduction. And it is a great pleasure for me to attend this one for Asian Pacific Analysis and PDE seminar, and to speak here, and thank also to Daniel for his hard work to organize this wonderful seminar. So today I will talk on some recent work joined with Chang Wei at ANU on a sharp lower bound for the first Steklov eigenvalue. So my talk will contain first overview of eigenvalue lower bound, and then we introduce the Steklov eigenvalue and review some Steklov eigenvalue estimates, and then we will present our results and our proof. So a famous theorem due to Lichnowitz and Obata says that if you have a closed remaining manifold whose ridge curvature is bounded below by a constant, a positive constant, and then its first eigenvalue, non-trivial eigenvalue, is bigger or larger than nk. And here this lower bound is sharp because equality holds if and only if the manifold is isometric to the round sphere with radius 1 over square root of k. And the method to prove this theorem is nowadays very seems not very hard, and is based on two kinds of methods in PDE. So one is maximum principle, and the other one is integral method on Bochner's formula. So here I present a quick proof. So here is the proof on the integral method. So we have the following Bochner's formula. So if you integral the Laplacian f squared minus the Hessian f squared, then you will get the integral of Ricci on gradient f. And then, so this is just integral form of the Bochner formula. So I think most of us are familiar with this Bochner technique in PDEs. So when you're using the Cauchy-Schwarz inequality, so Hessian f squared is larger or equal to 1 over n Laplacian f squared, and the Ricci lower bound assumption, and then you achieve it. The left-hand side you will bound it above by the Laplacian f squared, and which is so when f is the first non-trivial eigenfunction, then this is lambda 1 square f square. And the right-hand side of Bochner will give you a lower bound, n minus 1k. And because f is the eigenfunction, so the integral, the Dirichlet energy here gives you the lambda 1 and lambda 1 times the L2 norm of f. So then you just eliminate everything on both sides. You will get the lambda 1 lower bound and k. Okay. And so when you examine the equality, so then you will see that the Cauchy-Schwarz inequality here will become an equality. So then you will get tensor type equation, that is the Hessian f equals to some minus kfg. So that is the Hessian f is proportional to the metric on a closed manifold. And Obata examined such kind of equation on a closed manifold, and he shows that this a closed manifold which admits a solution to this equation must be the round sphere. So then that finished the equality characterization. So this is the first eigenvalue for closed manifold. So for other kinds of eigenvalues like the Dirichlet energy, Dirichlet eigenvalue or the Neumann eigenvalue, so that is when you consider a compact remaining manifold with boundary, and really shows that if you still have a positive lower bound of Ricci, and you have a mean convex boundary, that is the mean curvature of the boundary is non-negative, then you will have a sharp lower bound, which is still nk for the Dirichlet eigenvalue. And Chao Xia and Escobar, they show independently that if assume the rich positive lower bound and the boundary is convex, you have a convex boundary, then the Neumann eigenvalue will be bounded below still by nk. But here the equality holds in both cases if and only if M is isometric to the hemisphere. Yeah, and the proof is also relies on the boundary version of the integral Bochner formula, which is also called Rayleigh's formula. Yeah. So when we have seen that when you have a positive lower bound of Ricci, and then you have lower bound, positive lower bound for the eigenvalue. So when the positive lower bound tends to 0, that is, if you have just a non-negative Ricci curvature manifold, then what happens? Then Li Yao first examined this problem, and they show that the first eigenvalue can again be bounded, but with some other geometric quantities. Here it is bounded by a pi square over d square, and this this bound is eventually given by Zhong and Yang. And this lower bound is also sharp because it can be approached by a rectangle, very thin rectangles. And here you will see that equality can only hold if M is a one-dimensional one-dimensional case, that is one-dimensional round circle or a segment. And this is for Neumann or for closed eigenvalue. So for Dirichlet eigenvalue, when you have a convex domain in Euclidean space, and you have the eigenvalue for the Schrödinger operator with convex potential, especially for Laplacian operator. And then the first two eigenvalues, lambda 2 minus lambda 1, is so-called the fundamental gap. There is a very famous fundamental gap conjecture, and which was proved eventually by Andrews and Klantenberg. So that it says the fundamental gap should be 3 pi square over d square. And this number is again a spectral gap for the one-dimensional Laplacian. And in fact, before when we talk about the Neumann or the closed eigenvalue, in fact, that one is always the first non-trivial. So the trivial one is, the trivial first one is 0. So before all of this kind of estimate, you can view it as a fundamental gap. Yeah. So for Dirichlet one, so the fundamental gap is in fact, because you do not know that lambda 1 is 0. So you just have lambda 2 minus lambda 1. And for Andrews Klantenberg's results, so there is also some generalization to convex domain in the sphere. But it is also, I think, an open problem whether this kind of fundamental gap conjecture holds for non-negative Ricci curvature manifolds. Yeah, because there is some technical thing that they use, a very important thing, that's the log concavity of the first eigenfunction, which is unknown in manifold case. Yeah. Next, we come to the study of Steklov eigenvalue. So still we have a compact manifold with a boundary, and if you have a smooth function on the boundary and you take the harmonic extension of this boundary function, that is always solvable. So then you take, you consider the following operator, which is called the Dirichlet to Neumann operator. So that operator sends the boundary function to the normal derivative of the harmonic extension. Yeah, and it is easy to show that this Dirichlet to Neumann operator is a linear non-negative and self-adjoint operator. Yeah, and it has compact inverse. So then the classical spectral theory tells us this operator has discrete countable eigenvalues. Yeah, so that is we denote by sigma I. So the first, in fact, the first one, or we denote by sigma 0. The trivial one is 0 because we always have the trivial one, trivial eigenfunction, the constant one. Yeah. So we are interested in the non-trivial, the first non-trivial one, sigma 1. And this kind of eigenvalues was first considered by Steklov in Euclidean space. It has some physical motivation, which I will not explain here. So now the Steklov eigenvalue is just you have a harmonic function. So now we consider we have a compact Riemannian manifold with boundary. Then you have a harmonic function in interior, and you have the normal derivative of this function is equal to some constant sigma times f on the boundary. And similar to the other eigenvalues, so Steklov eigenvalues still have the following min-max characterization. So the first eigenvalue is given by the infimum of the digital energy in M divided by the L2 norm of F, but over the boundary. So different from the eigenvalue we see we considered before. So here the boundary L2 norm is on the boundary of sigma, and the infimum is taken for all C1 function with the vanishing boundary integral here. So again, the case Steklov eigenvalue, again, you have this min-max characterization. Okay, so for Steklov eigenvalue, so there is a few domain, so you can really compute its Steklov eigenvalues explicitly. So for the unique disk in R2, so the Steklov eigenvalues are all integers. So each integers so has multiplicity 2, and the corresponding Steklov eigenfunction is in fact using the polar coordinates you can write in the following. And in fact, this can be computed in all dimensions. The computation is just using the separable of variables. And for n dimensions, you have all still the Steklov eigenvalues as all integers, but now you have a very complicated multiplicity here. And in fact, this multiplicity is just the dimension of all the homogeneous harmonic polynomials of degree k. Yeah. And this is just these are all the Steklov eigenfunctions. Yeah, this is the model we look at, so the Bohr model or the disk model. And so Taylor first investigated the lower bound for the Steklov eigenvalues, and he proved that if you have a planar domain with boundary geodesic curvature has having a positive lower bound CC, and then the first non-trivial Steklov eigenvalue is larger or equal to C. And here, this lower bound can be attained by the disk with radius 1 over C. And in fact, this equality holds. So only if this this should be the domain is the disk of with radius 1 over C. And Escobar generalized Taylor's result, and in fact the method is the same. So to the manifold case, so to the non-negative manifolds of non-negative curvature, and still he assumed the geodesic the boundary geodesic curvature is larger or equal to C. And then you will still have the first non-trivial Steklov eigenvalue bounded by this C. And equality holds when if and only if M is isometric to this B2 1 over C. And for higher dimensions, Escobar showed that when you have non-negative ridge curvature, and also the boundary principal curvatures are always are bounded below by C. And then he showed that this first sigma 1 should be larger, strictly larger than C over 2. And in view of the Lichnowitz-Obata's theorem, this is somehow very okay. So sorry everyone for the interruption. So let's. I think I just talk to here, right? So Escobar proof that when you have non-negative ridge curvature and the boundary principal curvature lower bound, C, then you will have the first eigenvalue lower bound is C/2, and then he conjectured that this lower bound should be larger or equal to C, and compared to this Lichnovitz or Bata theorem. And in fact, this after he proved the C/2 lower bound, so there's no more progress for this topic. So this is even unknown for Euclidean space, for Euclidean domain. Okay, I would like to call your attention to some several developments for the parametric upper bound for Steklov eigenvalue recent years. So in 2 dimensions, Weisstock proved that for a simply connected domain, so then the sigma-1 times the length. So this one is normalized Steklov eigenvalue. You can view it when you fix the boundary. This one is scale invariant. And then this scale invariant Steklov eigenvalue will be bounded by that of the unit disk. Okay, and equality holds when you have a conformal diffeomorphism to the unit disk, so that phi is when you're restricting on the boundaries and isometry. And recently, Fraser Schoen investigates this Steklov eigenvalue, and they found general bound by genus and the boundary components. And in fact, when they consider the annulus type domain, annulus type surface, they can really get they can really characterize the maximal metric. That is the metric which obtained by the induced metric of the critical chitinoid in three balls. And in fact, they can show they can characterize the maximal metric. So if you consider the sigma-1 times L as a function on the manifold M, on the surface M with the metric G, and you take all the smooth metric, you maximize or you take the supremum of the metric, then whether this supremum of this problem exists, this is very important question. And if they prove that if this maximal metric exists, then there will be independent eigenfunctions, so that this eigenfunctions gives you conformal free boundary minimal immersion. And that to consider this kind of maximal metric problem, you will find more and more examples of free boundary minimal immersion in the ball. Yeah, and recently, quite recently, I think just the last month, Mathieson and Pettis, they proved that for any topological type surface, so this kind of smooth maximum metric exists for the first Steklov eigenvalue. Yeah, and for higher dimension, this problem is considered in Euclidean space. And Brock showed that he considered this scale invariant first eigenvalue, but now this is sigma-1 times the volume of 1 over n. Okay, it's not the boundary length or boundary area. So this one has an upper bound, which is bounded by that of the unit ball. And later, Butcher, Ferrona, Nietzsche, Trombetti, they considered the scale invariant of sigma-1, which is sigma-1 times the area of 1 over n minus 1. So this one is just in 2 dimensions, sigma 1 times the length, the boundary length. So they prove that for a convex domain, you will have this isoperimetric inequality. However, Fraser-Schoen show that this is this quantity sigma 1 times area to the power 1 over n minus 1 cannot be bounded by that of Bohr. So they can construct some contractible domain, so which is not convex. Then then you can show that this kind of scale invariant quantity is bigger than that of the unit Bohr. Okay, so this is something about isoperimetric upper bound for Steklov eigenvalue. Yeah, and there is some kind of comparison of the Steklov eigenvalue with the boundary eigenvalue. So Wang and Xia, this is Chao Xia. So they prove that when you have rich lower non-negative rich and boundary curvature larger or equal to C, then sigma 1 can be estimated by the quantity, the function of lambda 1 here. And Kapuskin showed that when you assume non-negative Weissenberg curvature, the second Weissenberg for curvature, then you have sigma k, the case eigenvalue, Steklov eigenvalue is bounded by the case boundary eigenvalue. So here the Weissenberg curvature is something in the Bochner formula for the some curvature term in the Bochner formula for P forms. So here is for 2 forms. Yeah. Okay. I think let me come back to our results. So we in fact we proved the following thing. So if you have a compact n-manifold with boundary, and if you assume the non-negative sectional curvature, so which is a stronger assumption than non-negative rich curvature, and still we have a boundary principal curvature has positive lower bound, then you will have sigma 1 larger or equal to C. So this is for all dimensions. And that means recall that Escobar conjectures that this kind of result should be true for non-negative rich. Okay, so here we show his conjecture in the case of non-negative sectional curvature. So especially we confirm this thing for Euclidean domains. So if you have a Euclidean convex domain or strictly convex domain, then the first Steklov eigenvalue will be bounded below by the minimum of its boundary principal curvature. Yeah. Slides, I talk about the results on the some progress on Escobar conjecture. So that means when you have non-negative sectional curvature, then it is okay to show that the sigma 1 is bigger or equal to C. And in this results, under the same assumption, we get the comparison of sigma 1 and lambda 1, as well as sigma k and lambda k. So compare with the previous results. So Wang and Chao Xia's results, we have they assume only rich curvature lower non-negative, but we get stronger conclusion. And compared to Kapuskin's results, so we have different assumption. So but the same conclusion in higher dimension and better conclusion in 3 dimensions. So I think it is I need somehow I just skip the part of review of Penner Escobar's method in 2 dimensions or the Escobar's method in higher dimensions. I just come back to our directly to our proof. So in fact, the most important ingredients we use is the following weighted Rayleigh formula. So we still use the integral method. And but the usual integral method in this slide, you will see that Escobar in fact used this one, and he showed that you can only use this classical release formula to get sigma 1 larger than C/2. And with weighted Rayleigh formula, so that is we proved this one is proved by Guohuan Qiu and me. We have additional smooth function v here, and when you integration the Laplacian f squared minus Hessian f squared times v, and you're using integration by parts, you will easily get the following identity. And we remain with some interior term, which is given by Hessian v minus Laplacian v and plus v Ricci. And there is another ingredients, which is the Poisson-Aif identity. So when you times the Laplacian f with gradient f gradient v, and then you integrate it by parts, you will get this kind of identity. And of course, we need to choose some special v for our problem. So our choice of v is rho minus C/2 root square, where rho is the distance function up to the boundary. So there is several important properties for this v. So first, v is positive function, and second, v is Lipschitz function, but it is only smooth outside the cut locus of the boundary sigma. Yeah, and on the boundary, v is easy to see that v is 0, and the boundary normal, the normal derivative of v is -1. Yeah, that means on the boundary, so v has very nice properties. And the most important thing is for this v is the Hessian comparison. So Heitzer-Kasher proved that when you have non-negative section and boundary principal curvature lower bound, positive lower bound, then you have Hessian v is less or equal to minus CG. So G is the metric, and outside the cut locus. This is the Hessian comparison theorem. And so how about the global thing? So inside this cut locus, what happens? So in fact, Kasu showed that V is in fact minus C concave in the sense of Hongxi-Wu. And this kind of minus C concave is you do not use the Hessian because you cannot take V is not differentiable, but you use the second order approximation of this V, and then you will see that this kind of limit inf is less or equal to minus C for any directions. And by a smooth approximation or Greener-Wood's approximation, you will find a smooth function V epsilon. So this one is smooth all among the manifold M, and the Hessian V will be less or equal to minus C minus epsilon G. So here you have a small epsilon. You lose something, but lose very epsilon thing, but you get a smooth function. The better thing here is that you still have on the boundary, because this convolution after a gluing of V by a cutoff function, you still have the boundary value is the same with V. So now we come back to this two integral identities. So when you choose the v or v epsilon, which is smooth function here, and what we have. So on the boundary term here, v is 0. So this boundary term vanishes. And for this boundary term, v, the normal derivative of v is -1. So here you get minus the gradient f squared. So totally, you get the following. So when f is harmonic, you will see that the left-hand side is less or equal to 0, and the right-hand side the only remaining term is this one and this one. So which is the boundary integral of minus gradient f squared, and the Hessian v minus Laplacian v of gradient f. And for the positive identity, still similarly you have this identity. So recall that for the Steklov eigenvalue, we have no information of the boundary integral of gradient f squared. So we just eliminated it by using the previous two information. Then you will get the following. So the normal derivative of f squared integral is larger or equal to minus Hessian v integral. And here Hessian v, you know that it is minus Hessian v is larger or equal to c minus epsilon. Then you will get this one. And if you have a Steklov eigenvalue, then the Dirichlet energy will give by sigma 1, then L2 norm of the boundary, over the boundary. And then the right-hand side, you will give sigma 1 times the boundary L2 norm. And then the left-hand side is just the sigma 1 squared. And you let epsilon goes to 0, we will conclude the lower bound, the sharp lower bound sigma 1 larger or equal to c. Okay, so the main idea is just you use the weighted formula here, and the weight we choose is exactly given by some function on the distant function, and we satisfy some Hessian comparison theorem. Okay, and for the upper bound of sigma 1, you just use only the weighted really formula. You will get this. Yeah, I will speed this. And the last thing is the equality characterization. So it comes to Obata type theorem. So when you assume the rich non-negative and the mean curvature positive lower bound, then you will, and for the manifold, if there is some function satisfy the Hessian vanishes and the normal derivative is CF, then omega is isometric to a Euclidean ball with radius 1/c. And in fact, here the curvature condition here, the rich non-negative and the mean curvature lower bound, this kind of curvature condition is necessary for this characterization. Because if there is no such kind of curvature condition, there might be other manifolds admitting the solution to this kind of equation. So recently, Chen Xuejiang Chen, Mi Jialai, and Fang Wang studied such Obata theorem in general. So there's no such kind of curvature condition. Then maybe there are some other web product structure. Yeah, you can only conclude that there is a web product structure for this manifold. Yeah, for our proof, this is an ideal deductive angles. So using the Hessian F is vanishing, so that you get a gradient F is Killing vector field, and this Killing vector field will gives you a product manifold. On the product manifold on based on some level set of f. Yeah. And then you may write the boundary as a graph over this level set, and by some computation, you will see that in fact you will see that this n0, the 0 level set, must be an n-1 Euclidean ball. Okay, and then you will finish the proof. Okay, lastly, I want to mention some open questions. So, of course, first, whether the Escobar conjecture holds for non-negative reaching. Yeah. And another possibility is that whether it is possible to show Escobar conjecture for rich non-negative and the mean curvature lower bound. Yeah. Because our V, in fact, if you under this condition, you will see that the weighted function, the V satisfy Laplacian comparison. And the last thing I want to mention that if C goes to 0, then this lower bound is trivial. So how to estimate sigma 1 by other geometric quantities? So compared to this Li Yao Zhongyang's estimate. So using the diameter or in radius to circumradius to estimate the lower bound. So that is unknown. Okay, thank you for your attention, and sorry for the.
Thank you very much, Chao. Look, I'm sure it's not your fault, but that's something we'll have to try and iron out in future talks. So we lost some time there, so we still have some time for questions. If anyone would like to ask this question, I think you can just raise your hand. There should be a button down at the bottom to allow you to do that. While people are thinking, I have a question or two. So you're using this weighted integral formula to, I mean, so you use this and you managed to get rid of this extraneous factor 2, which was there in the previous formula. So Escobar lost a factor 2. It occurs to me that there are other problems where you have similar Riley identity proofs, but where you also lose something. And the most obvious one is the Yao conjecture on the first eigenvalue for a minimal surface in the sphere. Have you looked at all of that question, and whether you can use your weighted formula?
We have looked at this question. So maybe this kind of weighted Rayleigh formula has some will play some role in this question, but it is far away from resolution of Yao conjecture, in my opinion, because in fact, for this Escobar's conjecture, the model case or the good thing is that you want to characterize the ball, but so then very important thing is that this kind of Obata's theorem tells you if you have some condition on the Hessian F proportional to the metric, then you will get such kind of round ball or round sphere. But for minimal surface in S3 or Sn, so the minimal surface can be very complicated. I mean, it's not that simple. So maybe it is not, but however, in some sense, on minimal surface, there is really a good thing that is the position function. It's really satisfy the Hessian, I mean, xi, the coordinate function, xi satisfies Hessian xi equal to proportional to the metric, right? Yeah. But because minimal surface is, you can have any kinds of minimal surface. So I'm not, it might, in my opinion, it might play some role, but not, this is not enough.
Yeah, okay. Thanks. I think Julie has a question. Julie?
Yeah, so what's the picture in negative curvature spaces?
So, sorry, for negative curvature space?
Yeah, yeah.
So what kind of estimate you want?
So something with the Ricci curvature bounded, but by something like a negative number.
Yeah, recently I think I have seen some work by Xiaolong Han and Hao Tianwu and Kui Wang. They consider some kind of, but the estimate is upper bound estimate when you assume the non-positive sectional curvature. And that kind of upper bound still, the model case is still the round ball, the geodesic ball.
Thank you.
Okay, good. Are there any other questions that people would like to ask? So one other thing I was wondering was, at the beginning when you talked about the Lichnerowicz-Shobata theorem, you mentioned there are really two ways you can prove this. One is using integral formulae, and then you can also use maximum principal argument.
Right.
Do you know,
For
is
maximum,
there...
I think for maximum principle, that's in fact, this the typical the method for gradient estimate.
Yes.
So you can construct such a gradient u square plus some cu square or ku square, and then you will show that this kind of function is subharmonic, and because on closed method it must be constant. Sorry,
yes,
it must vanishes. So yeah. Then you will show it.
Did you look at all whether there is a maximum principle version of your argument? I mean, it seems to me that your weighted formula.
Steklov. You mean for Steklov?
For Steklov, yes,
yeah. In fact, that's what I skip in my slides.
Oh, I see.
So this is for two-dimensional case.
That's Escobar.
So Kenner and Escobar show this using the maximum principle. But because now you have the information on the boundary, because you only have the normal derivative information. So when the dimension is higher, then this information is not enough.
Yes.
At least not that simple, right? In two dimensions, because you have only the boundary is just a curve, so you can parameterize by the curve parameterized by one dimensional, one variable function, and so everything when you use maximum principle, you can really set all things out so that you can get this positive lower bound.
Yeah, I'm wondering whether your weighted integral formula might correspond to applying a maximum principle to something like a gradient multiplied by a weighting function.
Yeah, okay. So
control the boundary in the same way.
In in fact, we have some local form for this weighted Rayleigh formula, but the local form is in fact is some divergence type. So it's not Laplacian of some function.
Yeah.
It is somehow is you can have some weight in this divergence type. So because in fact every integral formula you can really localize it. So
yes.
But for this kind of localized version, how to use the maximum principle, I'm not sure whether this is useful or not.
Okay, wonderful. Thanks very much. Okay, are there any other questions? If not, then I think you should all have received an email inviting you to the coffee break afterwards. So please join us there when you can do.